Well, let's, before the last talk of today, let me announce that for the participants of the program, we are putting the lecture notes and the slides both in the office of Ana Garcia in the app Sococo, if we are using it, and we are creating also a Slack channel with the where you would find the lecture notes and the slides. That being said,
thank you so much. So I'll just start by briefly reviewing the definition from time. So we have the non-negative Grassmannian, sometimes just referred to as positive Grassmannian for short, which is the set of all k-planes in an n-dimensional real vector space where the Plücker coordinates up to, say, a global change of sign can be taken to be all non-negative. And then we have the totally positive Grassmannian, which is the elements of the Plücker coordinates are all strictly positive. And as I mentioned before, this was only defined like this in the early 2000s, but interestingly, one can use sign variation results of Gantmacher and Krein from the 1950s to give another description of these spaces. So let me first make a definition. So if we have a vector v in Rn, we'll let var of v be the number of sign changes in the vector v, where we view v as a sequence of n numbers, v1 through vn, and ignore the zeros. Okay. So I'm just going to read the components of my vector from left to right. I ignore the and I just count how many times the sign changes. And then as a related definition, var bar of v is going to be what I get if I now arbitrarily assign a sign to each of the zeros and look at the sign changes and then find the maximum possible number of sign changes I can obtain that way. So this is the maximum of the number of sign changes we can get after choosing signs for each component of the vector, which is 0. So as an example, if my vector v is 4, -1, 0, and -2, then var of v, I'm just counting sign changes after ignoring zeros. So I see one sign change from positive to negative here. And then I don't see any more sign changes. I ignore the 0 and I just have negative. So I only have one sign change. So this is 1. But on the other hand, if I'm computing var bar of v, if I want to maximize the number of sign changes, I want to think of this 0 as a plus. And then I see 3 sign changes, plus to minus, minus to plus, plus to minus. So that is var bar of v. Okay. And now we can give a alternative characterization of the totally positive and non-negative Grassmannian. And this was realized by Stephen Karp and is essentially a modern interpretation of old results of Gottmacher and Krein. So let's let V be an element in the real Grassmannian. And then the first statement is that V lies in the non-negative part if and only if var of little v is k minus 1 for all vectors little v in my subspace V, if and only if var bar of W is at least k for all vectors little w in the orthogonal complement of V. And I need to also exclude 0 because var bar of 0 is large. That's the first statement. This is a characterization of the non-negative part of the Grassmannian. And the second statement is a characterization of the strictly positive part. And so V lies in the strictly positive part if and only if var of V is at most k minus 1 for all V and V, if and if var of W is at least k for all vectors W in the orthogonal complement of V. Again, removing 0. So, so this is a nice, simple interpretation of the positive and non-negative Grassmannian, and I just wanted to introduce it here because when we start talking about the amplituhedron in the next lecture, this variation will again be useful. Okay, so last time I was talking about the positive cell decomposition Grassmannian. So let me just recall that for M, a collection of element subsets of the numbers 1 through n, we define the positroid cell to consist of all elements in the non-negative Grassmannian where the Plücker coordinate pi of v is strictly positive if and only if I lies in this collection. And this subset is a positroid cell. And last time we showed how to describe cells using Lebesgue graphs. So these planar bicolored graphs embedded in a disk. And we showed how to characterize points of the cell using almost perfect matchings or dimers, to use the word of that Charlie's been using in his lectures. So this was one way to describe the cells. And now a second way that I want to describe is using the combinatorics of decorated permutations. And again, these objects were first appeared in the 2006 preprint of Postnikov. Okay, so what is a decorated permutation? Decorated permutation on the numbers 1 through n is, first of all, a permutation on n letters whose fixed points are colored one of two colors. And we'll sometimes refer to them as black fixed points, or sort of synonym for black will be loop, or we'll call the other class white or co-loop. And the calling them black or white is useful when we're also thinking about Playback graphs, and calling them loop and co-loop is useful when we're thinking of them in terms of matroids. So I'll write pi of I is I underline for a black fixed point, and pi of I is I overline for a white fixed point. And then I need one more definition, which is that an anti-exceedance of the decorated permutation pi is a letter I in 1 through n, such that either pi inverse of I is greater than I, or pi of I is I overline, which was our white or co-loop fixed point. Okay, and the reason why I'm defining this statistic is because we want to associate decorated permutations to cells in the totally non-negative Grassmannian, and so we need both a k and an n for our GKN. So you see the n right here, and the k is going to be coming from these sequences. So we say that a decorated permutation on the numbers 1 through n is of type kn if it has k anti-exceedances. So as a small example, if pi is the permutation written in list notation as 3, 2 underline 5, 1, 6, 8, 7 overline 4, then it has a loop at 2, co-loop at 7, and it has 3 anti-exceedances, which are 4, 7, and 8. So this decorated permutation is going to have something to do with a Grassmannian of 3 planes in 8 space. Okay, so now I want to explain how that works. So I want to explain concretely how to label positroid cells by different permutations. Okay, so let's start with an element of the totally non-negative Grassmannian. So let's let C be a full rank K by N matrix. Let me label its columns by C1 through Cn. Whoops. Okay, and this is a matrix representing an element of the non-negative Grassmannian. And now we're going to associate a decorated permutation, pi, so it depends on C, so I'll write pi or pi sub C, of type Kn as follows. So let's set pi of I to be the number j, which is the label of the first column j I see, such that column I is in the span of columns I+1, I+2, up through j. And so what I'm doing when I compute pi of I is I'm going to look at my ith column of my matrix, and then I'm going to start looking at the next columns in order, the I plus first, I plus second, and find when is the earliest place such that CI is in the span of those columns just after it. And I want to view the columns as sort of wrapping around on a circle. So columns are going to be listed in cyclic order, and we allow wrapping. And there's two special cases here. So if column CI is the 0 vector, then in matroidal terms, we would call this a loop. And so we're going to set pi of I to be I underline, which was also called a loop. And special case is that if CI is not in the span of the other vectors, so in fact, when you do this process of looking at the columns after it, and you have to wrap around and actually include I in your set in order to get CI in the span, then we set pi of I to be the other kind of fixed point. So in matroidal terms, this is saying that column I is a coloop. It lies in every single basis of the matroid. So let's do a small example. If C, the following 2x4 matrix, we can first of all check this does represent a point in the non-negative Grassmannian, and pi sub C is going to be a permutation that will now compute. So to compute pi of 1, we need to, so we're starting with column 1, and we now have to look at the columns coming after it and find out when column 1 lies in their span. So column 1 is certainly not in the span of 2, but it is in the span of columns 2 and 3. So this is 3. And now if we want to figure out what's pi of 2, we look in our second column and we ask, okay, is column 2 in the span of the third column? No. Is it in the span of the third and fourth columns? Well, no. Is it in the span of columns 3, 4, and 5? 3, 4, and 1. The answer is yes. So that's a 1. Okay, and then now let's figure out what's pi of 3. Well, column 3 lies in the span of column, and so this is a 4. And now finally, let's go to 4, and now we ask, now we have to wrap around the circle. We ask, is column 4 in the span of column 1? Well, no, but it is in the span of columns 1 and 2. So we put 2. Okay, so that's how we associate a permutation, decorated permutation, to a matrix. Okay, so now I can write down a description of a positroid cell in terms of decorated permutations. So given a decorated permutation pi of type Kn, we define sub pi to be the set of all points in the non-negative Grassmannian. The associated decorated permutation is pi. And then the statement following Postnikov's 2000 preprint is that this is a positroid cell and all positroid cells of the non-negative Grassmannian have the form S pi for some pi of type Kn. Okay, so in my previous lecture, I discussed positroid cells and I described them in terms of Playbook graphs. And now I'm giving a different description in terms of decorated permutations. And so, of course, the natural question is, how does S pi relate to the positroid cells that we associated to Playbook graphs? So that's the question that I want to answer now. And the answer is sometimes referred to as rules of the road, but this is also known as zigzag paths in the dimer literature. Okay, so let's let G be a reduced Playbook graph with boundary vertices 1 through n. And now for each boundary vertex I, we're going to follow the path along edges of G, which starts at I and then goes out along the first edge incident to I, and then starts turning based on whether it sees a black or a white vertex. So it turns maximally right at each internal black vertex and maximally left at each internal white vertex. So I'm going to show a picture in a moment. Actually, maybe I should just draw the picture right now. So here's a Playbook graph. Okay, so this recipe I've written down is going to give us a permutation. So we start at a boundary vertex I. Maybe I should just show it. Let's start at our boundary vertex 1 and follow these rules of the road. So I go out along this edge, it's white vertex, and so I turn left. Then next I see a black vertex, so I turn maximally right. Then I see a white vertex, so I turn maximally left, and I arrive at the number 8. Okay, so just to continue the formal explanation, the path ends at some boundary vertex. It's some number which I call pi of I. And now the fact that G is reduced implies, and this is a non-trivial fact, but this does imply that each fixed point of pi comes from a lollipop. And so now when we have when we have fixed equivalently lollipops, we'll color fixed points black or white on that lollipop. Okay, so now continue our recipe here. If we start at 2, we'll go out here, see white, we turn left, see black, we see right, see white and turn left, see black, turn right, turn left, and we get to 5. And let me not do it all out, but I'll point out that we do have a black lollipop here, which means that 6 will be a fixed point, which I think I denoted by underline. So if you follow the recipe, then you will get the following permutation. And this permutation has anti-exceedances. Okay, so now there's a very important theorem, which one might call the fundamental theorem of reduced Plabic graphs, which says the following, that G and G prime be reduced Plabic graphs. Then G is move equivalent to G prime if and only if the decorated trip permutation pi G is equal to the decorated trip permutation pi G prime. So this this decorated permutation that we associate to every reduced Plabic graph is the right invariant, for Plabic graphs. And just a word about the proof. One direction of this theorem is easy. It's easy to show that the local moves preserve the trip permutation, but the other direction is quite hard. And so Postnikov's 2006 preprint has a proof which is quite technical. I'll just mention that that one can find another proof that I think is easier to read, but I leave that to others to judge. We have another proof in chapter 7 of our book on cluster algebras, which is all about Plabic graphs. And this proof uses as an important tool Dillon Thurston's triple diagrams. So Dillon Thurston has some objects called triple diagrams, which are very closely related to Plabic graphs. And for proving some properties, it's actually easier to work with triple diagrams than Plabic graphs. And we've found it to be the case. For this theorem. Dillon, in his own paper, which actually Dillon's paper came out at roughly the same time as Postnikov's, and he has a statement very similar to this one. So anyway, so if you want to really understand the proof of this theorem, then it's helpful to work with triple diagrams instead. Let's see. Oh, sorry, for completeness, I need to make one more remark, which is that one can realize each decorated permutation of type Kn as the permutation coming from some reduced Playbit graph G. And so the decorated permutations are in bijection with the move equivalence classes of reduced Playbit graphs. Okay, are there any questions about that?
Lauren, there was a question in the chat about the example you did. Should it be 417 at the end?
Oh. Yes, certainly, because what I wrote was not a permutation, so there's definitely a mistake. And let's just check that 9 really goes to 7. So 9, turn right, then turn left, turn right. Yes, thank you.
Excellent, thank you.
Okay, so now I just want to say a word about cluster structures on the Grassmannian, because they're closely related to this combinatorics. And it was a early theorem of Jean Scott from, I think, 2003 or 2004, which is that the coordinate ring of the affine cone over the Grassmannian has a cluster algebra structure. And if you want to write down a cluster for the Grassmannian, this is the easiest way, I think, to do so. So I'm just going to show it with an example. This will be for the Grassmannian of 3 planes in 7 space. And I'm going to draw a quiver where vertices are labeled by Young diagrams in a predictable way. I have the empty set here, and then arrows are like this. And I'll just, the frozen, let me just denote the frozen variables by highlighting them in blue, I guess. And now I want to identify vertices with Plücker coordinates. So we're going to map the Young diagrams in this picture. So all these Young diagrams are contained in a 3x4 rectangle. And we will map them to Plücker coordinates, pi, with I a 3-element subset of the numbers 1 through 7. And it's this sort of standard identification where we identify a Young diagram with the vertical steps of the path along its border from the upper right to the lower left of the 3x4 rectangle. So as a small example, how do I read off the Plücker coordinate associated to this? Well, I will put that Young diagram inside of a 3x4 box. And now I will label the southeast border, and I will map it to the Plücker coordinate whose K subset corresponds to the vertical steps in that path. Okay, so this is the easiest way to write down one seed for the cluster algebra. But more generally, if G is a reduced Sept graph with trip permutation pi kn, which is the following permutation, then we can get a cluster quiver for GRKN as follows. So we'll basically write down the quiver, which is dual to the Plabic graph. So let's say that this is my Plabic graph. 3, 4, 5. Check in this example that the decorated trip permutation is 3, 4, 5, 1, 2. And so I'm going to do two things. I'm going to label faces of G by Plücker coordinates, and I will also write down the dual quiver to this graph. So let me first explain how to label faces by Plücker coordinates. And this is again going to use the rules of the road, which in my convention say turn at a vertex, at a left vertex, turn left at a white vertex. So for each number I, I'll put an I in every face to the left of the trip, which goes from I to pi of I. So let's see how that works in an example. My trip starting at 1 turns left at white, right left at white. So there's two faces to the left of this path. And so I will put a 1 face. And then similarly, if I start at 2, I'll go out here. I'll turn right, turn left, turn right, and then left. And so left of this red path means what you see below. And I'm going to put a 2 in those 3 regions. So if you continue like this, then we'll get the following labeling of regions. And I'm going to identify these 2 element subsets with Plücker coordinates. And then to write down the cluster quiver, I'm going to add arrows as follows. So if I see a edge, a bipartite edge in my Plabic graph, I will draw an arrow and quiver like this. So, so first, vertices of my quiver will correspond to faces of the Plabic graph, and internal faces are mutable, and the ones at the border are frozen. So there's n frozen ones around the border, and then remember all of these labels I wrote down are getting identified by Plücker coordinate with Plücker coordinates. And then now I draw my arrows according to the recipe that I had here. So I'm drawing arrows so that I see white to the left. Okay, so what you see in red is the cluster. Okay, so now I can restate the result of Scott, which is that each one of these is a seed for the cluster structure on the coordinate ring of the affine cone of the Grassmannian. So we can get them from these reduced Plato graphs. Let me make various remarks about what's known. So in the case of two planes in n space, we get a type A cluster algebra, and the cluster variables are exactly the Plücker coordinates for GRKN with k greater than 2. The Plücker coordinates are a strict subset of the cluster variables, and in general, for k bigger than 2, the cluster variables are not well understood, but in the case k equals 3, there's some very interesting work of Fomin and Piliovsky, which gives a conjectural description of those cluster variables. And now let me say just a few words about generalizations of Scott's theorem. So by choosing G with a more general trip permutation pi G, the statement of Scott's theorem can be generalized to open Schubert varieties, and also a class called skew Schubert varieties. This was joint work with Christina Serienko and Melissa Sherman Bennett. And then this result can be generalized to open positroid varieties. This was done by Galoshin and Karp and Lamb. And actually, I want to mention that both of these depend on prior work of Bernard Leclerc. They depend on Leclerc's work on cluster structures on Richardson varieties in G mod B. So Leclerc gave a construction of a cluster subalgebra in the coordinate rings and showed in some cases it's equal to the coordinate ring. And there's been recent, so Leclerc's construction was conjectural in general, that the cluster algebra was the full coordinate ring, but there's been progress on Leclerc's construction. And there's work from the last year by Bernard Keller and separately by Etienne Maynard. So let me say This represents substantial progress on Leclerc's conjecture. One final remark I will make is that now back to the setting of playback graphs and positroid varieties. One thing that's very interesting is that every positroid variety, so I haven't defined positroid varieties, but these are varieties that are naturally associated to playback graphs G with more general trip permutation. And each of these positroid varieties has, in general, not one, but many cluster structures obtained by sort of relabeling playback graphs in an interesting way. And that's from work in the last year or so of Chris Fraser and Melissa Sherman Bennett. Okay, so just say this combinatorics of playback graphs leads to some beautiful ways to understand cluster structures on the Grassmannian and subvarieties. So I think that's enough for today, and next time I will start discussing the amplituhedron.
Thank you very much, Lauren. Thanks, Lauren, for this talk. Are there any questions or comments?
I have one question. Can I ask, please?
Yes, please go ahead.
Is there a way to describe all possible seeds of cluster variables in terms of Young diagrams? So, for example, you suggested one seed in terms of Young diagrams, and there is a clear pattern for this Young diagrams. They over some sub-rectangles of rectangle 3x4. So, is there such a general way how to see that it is a seed?
Yeah, that's a good question. I think in terms of the Young diagrams themselves, it's not that easy to see compatibility, but there's something called weak separation. Which is a notion for k-element subsets of the set 1 through n. Weak separation is a good notion for understanding compatibility of cluster variables, and it's the appropriate generalization of triangulations of an n-gon to this bigger setting. So for G2n, the clusters can be described in terms of triangulations of an n-gon, and two diagonals in an n-gon represent compatible cluster variables if they are non-crossing, if these two diagonals don't cross each other. And weak separation is the generalization of this, where you generalize from 2-element subsets of 1 through n to k-element subsets of 1 through n.
Okay, thank you.
Are there any further questions or comments? It doesn't seem to be the case, so let's thank Lauren once again for this talk and all the speakers of today. Well, that being said, I think we will finish for today. We'll let the participants of the program in Cambridge to go to a formal dinner soon after this. And for all the rest, we'll see each other tomorrow. Thank you very much.